Bismillahirrahmanirrahim. Welcome to Easy Learn, and this is episode 15. By chance, I write mistakenly episode 14 on today's sheet, but it doesn't mean that it is again the episode 14. You are on the right episode, that is the 15. Anyway, before going to start today's lecture, I just want to recap what we are discussing in the previous section. In the previous episode, we were discussing the resistive parameters after completing the parameters of capacitive and the inductive with the help of examples. In the previous episode, we discussed the first two basic analysis of any circuit steps. As you know, basically three steps are needed for any type of the circuit. Suppose we have an inductive circuit or a capacitive circuit, or the third and the final category like the resistive circuit. We need to do the three steps. The first one is the physical phenomena that is completed in the previous episode, and the second one is the, of course, field interpretation, where we discussed the electromagnetic fields, and that was already wrapped up in the previous lecture. And for your information, I just want to recap the charge density, current density J is equals to sigma E. This formula that we already discussed in the previous episode, that is sigma. This is the lowercase sigma letter charge. Then that basically it is used for the conductivity of the substance. Like for example, this is the material that we are discussing right now. The conductivity of this substance is represented with the help of sigma, the lowercase Greek letter sigma. J is equals to sigma multiplied with E. So this is what we already discussed in the previous episode. This is the modified form of the Ohm's law, and this is used for the interpretation and the analysis of the field concepts, because you know this is here electric field. This is very important too. If we have the current is flowing through a system, there with having a length L, there must be an electric field around it. And if a uniform current is flowing through the cross-sectional area that is represented with the S, suppose it has a uniform cross-sectional area throughout the entire length L, and the uniform or a specific current is flowing, constant current is flowing through this, then there must be a same and exactly equal pattern will be seen throughout this surface with length L, which is having the same constant area. So this formula is valid all the surface. But right now, if we have a simple geometry, let's suppose this is a simple geometry that I had drawn here. This is a simple geometry, but the complex geometry case is this is a complex geometry. This is a complex, because right now if we discuss here, this is the area. Here the area is far more than the previous this section. The area between these two sections is not exactly the same. So in this length L, the area is actually varied many times. We had seen this variation. What does it mean? It actually means that this is a complex geometry when the current is flowing through this area, because this is the surface is no longer a smooth or a constant, a steady state. So it means that when the current is flowing, there may be changing in the pattern of the electric field throughout the length L. For example, let's suppose here we have this type of electric field, but when we go to this place, there is a different and a quite unique scene is created here. This may be sometime create a complex situations for the ruling parties. What we are going to do here, this may be a complex case for us. So what we need to do, but right now for just the beginning, we are going to solve the discussion and starting the discussion with the basic simple parameter, that is the constant parameters. This is a geometry that is the simple geometry having a uniform area throughout this length L, and this needs to be discussed in today's episode. If we want to relate the voltage and the current, we use this form V is equals to IR without the field effect. Actually, here we have an understood that the field is actually constant, so we can ignore this for just a moment. We can ignore the field, so the Ohm's law is actually becoming the V is equals to IR. But this Ohm's law, where does it come from? We are going to derive this and going to discuss in details first, and then we will also discuss in the last part of today's episode the summary and a very important and a beautiful diagram for different relations. Okay, this is Ohm's law also, but this is again Ohm's law. V is equals to IR, this is Ohm's law, no doubt, but what we already discussed is also the Ohm's law. So there are two different types and categories of Ohm's law. This is used for when we have the field, like here you can see we have a field, so this is the main reason we are using here. While this second category, this is used where we have a different types, like simply we want to relate the voltage with current, having we can ignore the field here because it is understood, maybe having a uniform area, having a uniform geometries. So V is equals to IR is really important. We are going to use this term, but first of all let us define the basic rules for going through. If the cross section of the conductor is uniform, the current and the current density are related by this equation. I is equals to integral J cos theta ds. Here you need to memorize this equation first in your brains before proceeding to the next section of this episode, because this is the relationship and the how we can relate the current with the current density, that is the J. So current is equals to integral J cos theta ds. Here you can see the limit S is sometimes written here in lower limit as a, this actually means that derivation is with respect to surface area, that is the means cross sectional area, and lower limit also indicates the limit of the cross sectional length or cross sectional area. So if it is a constant, we can simply ignore the length, we just write here it generally from S. But remember that this J and S, this is the dot product, that's why here cos theta, in the when we open the dot product, you know, cos theta always there. But usually we are going to use the maximum term. So J cos theta, in the case of the simple geometries, this simply cos theta have a value of 1, because cos theta maximum value will be 1. Why it has a maximum value 1? Because this theta, that is the angle between the length of the wire and the current flowing through electric field is uniform, so the current that is flowing into the length L making an angle 0 with the normal component of the length L. So actually due to this reason we are going to use the maximum case, that is the simply substitute here 1 and integration is also removed, so I is equal to JS. This is the main mainly we are going to use this for the simple case of the geometry's uniform area, and we are going to use this equation as a star equation. V is equals to EL, this is another equation. So first you need to keep in mind this equation, then first you need to keep in your mind this equation, because we are going to use this equation in our next page. And then second is V is equals to EL. This equation is valid only for those areas which have a specifically smooth geometry, uniform surface area. This is valid to those geometries. Okay, you cannot use this anywhere, anytime, anywhere. So what does it means? Here means that the voltage is equals to electric field multiplied with the length L, and remember that here we are going to only used where the length this is constant. Sometimes we have not the smooth geometry, so we can divide the portions, like I divide here. If we have a different type of the structure here, because we are going to divide this structure into small parts, small sections, and integrate them separately, then this formula is valid there. The what formula? That is v is equal to integral E cos theta dl. This formula that we discussed in the previous page, this formula is valid there, because the reason is, you can see there, this point to this point, it is approximately a constant having a uniform area. If this is a uniform area section that belongs to a uniform area, it actually means that L1 to L2, this electric field here in this region is constant, and this formula can be used for this section. Although this formula is no longer valid for this whole portion, and we cannot use this as a single phase, not using from this point to this point, because this is having a not uniform area, and no, rather than applying the formula for the single formula to whole section, we can divide into different portion. Like from this portion will be having a constant, this portion is constant, we can also take this a portion from here. So then combining all these portions and appending into the single section, like into the downloading of the IDM so you can find the overall area. So L1 and L2, 2 points are L1 and L2. This is the E, that is electric field. This is the sigma, that is always there for the conductivity, and J is our current density. So there is a small uniform section where we can apply this formula. This formula then converted into this type of shape, that is integration from lower limit toward upper limit. Integration from L1 to L2 means L1 and upper limit is L2 E cos theta dl. E is our electric field, cos theta, that is that you need cos theta, of course, angle, that I said that you can use the maximum case here also, dl. Okay, this is just this portion is just for the understanding. Now we are going to welcome back to again the discussion what we left in the last page. We discussed in the previous episode that this formula J is equals to sigma E. What this formula? This is the formula that is telling the field form, means the form of the electric field. This is the formula that relates the electric field with the current density, and this is called the Ohm's law. Now what we are going to do right now, actually our task right now is to put the value of the current density here, current density and electric field. Then this formula will be converted into a form of current versus voltage relationship, and if we are able to define a relationship and derive a relationship of current versus voltage in the resistive circuit, and this is the end of the circuit interpretation of the resistive circuit. So all we need to do is put the equation 1 and equation number star in this equation. So like J is equals to sigma E. Here first, one by one, first we are going to substitute the value of the E in this equation. Okay, what is the equation number 1? That is the V is equals to EL. Okay, ignoring the cos theta dot understood. V is equals to EL for the simple geometries. From here we can separate this electric field, the value of the electric field that is coming out from here, that is the E is equals to V over L. So the now we can substitute this value V E is equals to V over L into our main equation, that is J is equals to sigma E. So rewriting J is equals to sigma E, now this E is replaced with V over L here in the brackets, and when we are going to multiply it here, we need to separate the voltage from this equation. All we need to do is go the L length and the sigma conductivity move toward the other side, and then sigma goes into the, when L goes toward the other side, it is in the denominator and multiplied with the JL is equals to sigma V. Now sigma is going to other side, it will become V is equals to JL over sigma. This is the first thing, V is equals to JL over sigma. Now we need to also substitute the value of the J. As I said here, J is equals to sigma E. We need to substitute the value of the current density J and the value of the electric field E. So two values need to be put substituted in this equation. First one is already substituted, while the second one, that is the current density, now from the equation number star we are going to put in this. I is equals to Js, this is equation number star. From here J is equals to I over S, means this surface area is going to other side, that is in the denominator of I is equals to J over S. So J is equals to I over S. So this is the value of the J, and now this value of the J is going to be substituted in L. In J, V is equals to J L over sigma, rewriting the above equation, and now this we are going to replace this J with I over S. As you can see, I over S is outside the bracket, that is the that is come from the replacing the J. L over sigma. Now this is our equation number 4, and if we are going to just take the I from this, and all this is taken into the brackets, just separate the I outside of the bracket yard and others in the jurisdiction of the brackets, that is L over S sigma. V is equals to I L over surface area and the conductivity. But why we just consider the brackets here on L over this portion? Actually, the reason behind this is in the case of the simple geometries, we can easily substitute the value and calculate the value of the L and the surface density, surface area, and the value of the conductivity can be easily found and then multiplied with the current to get the voltage, or divided with the voltage to get the current, find the current. But what we can do if we have a little bit complex case like we discussed here, if we have this type of the case, how many portions we need to consider, how many types of the parts we need to consider for getting the uniform area. So we need to apply many formulas and then adding all the results to get the overall result. So it means that this is no longer valid and it is a complex case. This equation number 4 is very complex. We are going to define a rule to make it a little bit simpler. V is equals to I, and now this is called a resistive parameter. This is called a resistive parameter, simply resistance, and it is replaced with the symbol R, and the unit of the resistance is ohm, and the symbol is actually, this is the symbol, and the ohm is the unit, and R is the representation. V is equals to I, and now this is replaced, bracket is replaced with the R, and now it is much easier to substitute the value of the single term in this formula, as you can say R instead of substituting the values of the three terms, that is L divided by sigma S. So it is much easier, and maybe it is given to you. So multiplying the current with the resistance, we can easily get the value of the voltage. And if we have the complex geometries, we use the resistance directly in this formula and bypass the previous formula, equation number 4, skipping the equation number 4. So this is the Ohm's law, V is equals to IR, and that's how it is defined. That is the, of course, and but just before going to terminate this episode, let's take a look at the some beautiful terms, that is the V is equals to R dq over dt in terms of the charge. Let's suppose in a numerical the current is not given but the charge is given there. If you don't forget, I taught you there in the episode 1 that current is equals to derivation of the charge with respect to time. What does it mean? It means that if you are going to derivate the charge with respect to the time, it is easily the current. V is equals to R dq over dt. Here if we have a charge given in the numerical, putting the value here, we can get the voltage. Unit of the resistance is ohm, and there is an opposite term to the resistance, like this is actually resistance. Suppose this is what we want the current to flow here, and the behavior of the resistance is like that. This is the resistance that is coming against us, that is the barrier in our way, and this is taken as a resistance. While let's going toward another case, and again the current is flowing, but this time what we found in our way, there is another scenario here. Here we have like that. Here we have a push. This is called conductivity. We have a path that is supporting us, that is not against us, but that is with us. This is a case that is taken as G, means conductance. We are not going to replace giving a letter C to conductance, because it is already dedicated to the capacitance. Don't forget it. So G is used for the conductance, and it is supporting us, it is providing a path to go through, like there is a specific conductance of this material, that means how much free electrons. The conductance will be high if there are more availability of the free electrons in a material. Like this has a more conductance. Conductance and inductance are the opposite terms, remember that. This has a high conductance and low resistance, and if this is a circuit which has a very few free electrons, it has a low conductance but it has a high resistance. So these are the two opposite terms. So why not we are going to define a relationship, R is equals to 1 over G, or you can simply say G is equals to 1 over R, means reciprocal of each other. So unit is also again the reciprocal, that is mho, MHO. V is equals to IR, and we can also define the formula of the current from this relation, that is I, and converting this I towards the left hand side, moving this R from right hand toward left hand side, I is equals to V over R. And now 1 over R here, if we are going to just separate the voltage from this term 1 over R, because we want to replace this 1 over R with G, I is equals to GV. So this is the end, and this G is used when we have in the question, suppose conductance is given, not resistance, to find, and let's suppose the examiner asks you to find the current. What you can do there, you can easily find the current, but if you have the basic sense that G is equals to 1 over R, so just use this formula and enjoy solving miracles. Okay, here we have a very basic and a very beautiful for the understanding of different concepts. Someone I don't know the exact who did this first time, but there is a very famous diagram that is used in the networking analysis. So let's discuss this. Here this is a voltage and this is a current. There is a derivation d over dt with respect to time, and this is in the right hand side where my cursor is blazing. You can see easily stored magnetic field, while on the left side you can see stored electrical energy. There are the two different energies. On the right hand side this is a magnetic energy, while on the left hand side you can easily see there is an electrical energy. So here you can see different capacitive parameters: voltage, current, inductance, derivation, resistance, charge, and this is the flux. And this is here this means that voltage coming here, and this means charge coming here. So voltage multiplied by charge is equals to 2 WE. What does it means? W is a symbol that is from the episode 1 or 2. We used the symbol W there. So 2WE means that the stored electrical energy is equals to V multiplied by Q. So this is V coming from this side and Q is coming from this side. This will, by joining these two terms, multiplying these two terms, this will become the stored electrical energy. Here we have a V is equals to IR. What does it means? Voltage is equals to current multiplied by resistance. This is the is equal sign. So if you can if you are coming to this side, I multiplied R is equals to V. If you go through this side, I and V is equals to V and I multiply by multiplying these two terms, it will be, the result is power. This is a one way, mean you cannot come to back side again, but here you can come. V is equals to RI, I multiply R is equals to V into C Q, that is the formula for the charge is equals to Q is equals to CV in case of the capacitive circuit, and in case of the inductive circuit, psi is equals to L into I into L is equals to psi, that is the flux. And if we are going to the one-way circuit, that is the psi multiplication with the derivation with respect to time. If we are going to derivate the flux with respect to time, it is equals to voltage. We are not coming towards V is equals to d over dt, but we cannot come here in this way, like U-turn here from this way. We cannot take the U-turn. This is straight way, that is the arrowhead, means derivation of the flux with respect to time is equals to current, that is the wrong side. You are going toward this straight side. Derivation of the charge here, Q dot derivation becomes the derivation of the charge is equals to current, and current into L inductance is equals to psi. And here, and if current and the psi is multiplied, it will again become the energy, but this time M in the subscripts represents the mechanical energy, sorry, magnetic energy. So this is a basic diagram that is very much helpful for the basic understanding. So this is the finally we are here for after all the discussions. This is the summarized and the most important thing that we need to discuss. Here in this diagram we have different parameters. As you can see, we are going to discuss the summary of what we discussed so far. We had discussed the resistive, inductive and capacitive circuits. The most used formula and the basic relationship is here. We will first discuss the basic relationship for all the three circuits. Then we will use the voltage relationship of three circuits. Then we are going to define the current and the energy relationships, means their formulas. Because so far we discussed three basic circuits, so and these are the overall summary what we discussed, or all the formulas on a single chart, and this is very much helpful. I recommend you to write this formula chart on your notepad, on your notebook, on your computer's desktop page, to make sure to use it. It is in your handy, it is in your access, and use frequently whenever you need in the next time. This is how you can easily memorize the things, the best way to write by your hands instead of printing it. So this is the best way. So basic relationship of the, let's suppose we discuss the resistive circuit first, because so far it is a very much freshy circuit in our minds. The inverse of the resistance is conductivity, that is G. So now V is equals to Ri, that is the mostly used parameter, and basic relationship that is mostly used is the Ohm's law, V is equals to Ri. Again, voltage relationship, V is equals to Ri. In the subscripts, I usually write R. That means that this is belongs to this voltage, and the current belongs to resistive circuits only, not used for the voltage and the current of inductive circuits or the capacitive circuits. Same is the case if we are going to discuss the voltage relationship or the current relationship of inductive circuit, then we are going to write here L with the voltage and with the current in the subscript, to make sure that this is specially used for the inductive. But this is for your just understanding. So so it is not the basically necessity. You cannot write it, or you can I recommend you to not write, but just for understanding, that to not mess it with others terms. If you have enough knowledge and if practiced, then you cannot write it, just skip it. V is equals to Ri, I is equals to V over R. So this is again converting this formula into this side, that already discussed in today's episode, and I is equals to GV, that already discussed in today's episode, that 1 over R is equals to G and V as it is. So this is a new term, that is energy. Energy is equals to integral from prior to the switching time and present time. These are the limits that is changed according to the requirement, according to the situation. But you know, when we discussed in the any structure, in any simple simple system, general relationships will be written in the minus infinity to time, present time t. So you can also skip this in limits vi. So this is a multiplication of the voltage and the current will become the energy, and then an integral with respect to time t. So now inductive circuit, psi is equals to Li. This is the mostly basic relationship that the most widely used when we are going to discuss the inductive circuit. And then V is equals to L di over dt, that is discussed when we are discussing the inductive cases, and I is equals to 1 over L integral V dt. So this is the integration of the voltage here. And the energy, memorize all the things, because the next time you may find it difficult, and the best way to memorize this chart is writing and using it again and again. For example, solving the numericals, you may find it useful and you may need it. So this is the best way to memorize. W is equals to 1 over 2 Li square. So this is the third formula and last formula. Same is the case of the energy formula is 1 over 2 Li square, and L is representing the inductive parameters. Here the energy for the case of the capacitive capacitance. And once again, thanks to the inductive circuits, there is always in opposite terms in minds. The opposite to the capacitance is the elastance. Elastance is represented with the D, and D is equal to 1 over C. Q is equal to CV is the most widely term used in the case of the capacitive systems. And VC is equal to 1 over C integral minus infinity to time t IC dt. So this is the voltage relationship, and this is current relationship, I is equal to C dV over dt. This is the terms that we already discussed in the capacitive circuit, how these come from. You can watch the previous episodes if you forget them, or if you are new here. But the main thing is this chart, and finally the energy relationship is 1 over 2 CV square. These are all the terms you need to memorize, but the most important, the widely terms used is these two terms, voltage and the current relationship. That is the circuit interpretation of our discussion, that I focused mainly on these terms because this is the most widely used. If you forget about these terms, at least make sure you are starting memorizing the priority from this chart, middle terms, voltage and current one. I know that V is equals to IR or I is equals to V over R. This is the first one that you maybe already memorized them. So these four blocks, V, voltage and current of inductive circuit, and the voltage and current of the capacitive circuit, these are really difficult to memorize, but I giving you a very basic trick that each and every block is inverse to others. Like here, if you just memorize this term, V is equals to L di over dt. Suppose this is what you memorize, but the others are not easy to settle in your brain in the single try. Let's suppose V is equals to L di over dt. This is what you memorize, but this is you forget about what is the term of the current you've got in the exams. Suppose then all you need to do is starting from here, V, here I means inverse. What is the inverse of the voltage? In case of the current, I is equals to here L, here 1 over L, reciprocal. here derivation, here integration, here current, here voltage. So this is reciprocal, means if you memorize this term, you can easily convert this term into the current formula, and from this term you can also convert the capacitive one, and this is also inverse of these blocks are inverse of each other. Like here, if we are going toward the calculate the voltage, you know, you are getting the for the sake of the voltage, you are not going to replace the voltage with the current here, like in this case. So voltage is again voltage, because you are finding the voltage for the capacitive circuit, so voltage is not changing, is equals to L. Here it is L, now it is replaced with capacitance and inverse 1 over C. Here derivation, now here integration, here I also dt. And this block, first you need to write write this and then this, and from this you can write this one, or from this you can write this one. Parallel blocks can be written from previous blocks, watching previous blocks. Like here V is equals to I, 1 over C is C inverse, and integral is with derivation, I is with replaced with the voltage. So these are actually easier to memorize with the different techniques you may find. This is one of different techniques to capture the sketch in your brains. I'm just giving you an idea that it is not a difficult task. Whatever you want to do, just all you need to do is just repeat them again and again. And I recommend you to write this as I written on my sheet. Write this on your own papers, and make sure in the first and the starting page of your register. This is very important, the base of the network analysis. So stay tuned, watch and grow. This is the Easy Learn. I'm signing off. Thank you. Allah Hafiz.